Who says there are no open-minded scientists at NASA? A NASA scientist suggests you are living inside a hologram created by advanced alien species. What if everything you have ever done, or will do, is simply the product of a highly advanced computer code? Every relationship, every sentiment, every memory could have been generated by banks of supercomputers. This was the intriguing theory first proposed by Nick Bostrom, professor in the Faculty of Philosophy at Oxford University and founding director of the Future of Humanity Institute and of the Program on the Impacts of Future Technology within the Oxford Martin School. There are several scientists who subscribe to this theory. It has been previously reported on how Rich Terrell, director of the Center for Evolutionary Computation and Automated Design at NASA's Jet Propulsion Laboratory, suggested our creator is a cosmic computer programmer. This would imply that we are living in a holographic world and everything around us, including ourselves, is not real. Rich Terrell still stands by his opinion. Right now, the fastest NASA supercomputers are cranking away at about double the speed of the human brain, the NASA scientist told Vice. If you make a simple calculation using Moore's law, which roughly claims computers double in power every 2 years, you'll find that these supercomputers, inside of a decade, will have the ability to compute an entire human lifetime of 80 years, including every thought ever conceived during that lifetime, in the span of a month. In quantum mechanics, particles do not have a definite state unless they're being observed. Many theorists have spent a lot of time trying to figure out how you explain this. One explanation is that we're living within a simulation, seeing what we need to see when we need to see it. What I find inspiring is that, even if we are in a simulation, or many orders of magnitude down in levels of simulation, somewhere along the line, something escaped the primordial ooze to become us and to result in simulations that made us. The idea that our universe is a fiction generated by computer code solves a number of inconsistencies and mysteries about the cosmos, like for example our quest for extraterrestrial life and the mystery of dark matter. However, there are also those who think the matrix theory is flawed. The theory seems to be based on the assumption that superminds would do things in much the same way as we would do them. Professor Peter Millikan, who teaches philosophy and computer science at Oxford University, says, if they think this world is a simulation, then why do they think the superminds, who are outside the simulation, would be constrained by the same sorts of thoughts and methods that we are? They assume that the ultimate structure of a real world can't be grid-like, and also that the superminds would have to implement a virtual world. We can't conclude that a grid structure is evidence of a pretend reality just because our ways of implementing a pretend reality involve a grid. However, Professor Millikan does believe there is worth in investigating the idea. It is an interesting idea, and it's healthy to have some crazy ideas, he told The Telegraph. You don't want to censor ideas according to whether they seem sensible or not, because sometimes important new advances will seem crazy to start with. You never know when good ideas may come from thinking outside the box. This matrix thought experiment is actually a bit like some ideas of Descartes and Berkeley hundreds of years ago. Even if there turns out to be nothing in it, the fact that you have got into the habit of thinking crazy things could mean that at some point you are going to think of something that initially may seem rather way out, but turns out not to be crazy at all. Look around you. Your shoes, the tree, the Starbucks cold brew you're clutching, it's all very much right here in the real world. But what if the real world we live and move around in is just a computer simulation? Neil deGrasse Tyson, everyone's favorite astrophysicist, thinks there's a very high chance that not everything we know is just a hologram. He's just one of a growing number of people who believe it. Classical computers work with particles of information, or bits, that each exist as either a 0 or a 1. The reason quantum computers could be so revolutionary is that quantum particles exist in superposition, that is, they can be 0, 1, and all points in between, and only when you measure them do they decide on a value. The ability to contain multiple values simultaneously gives them the ability to crunch a million computations at once. But superposition ain't easy. The slightest interference can destroy that state of being many values at once, so quantum bits, or qubits, must be shielded from all external disturbance, a computer fan, for instance. What's more, they require low temperatures to operate. Bits have to start in their ground states to run an algorithm, during which they quickly heat up. Unless you want to wait around a while, you'll need a quick and efficient way to cool them that won't disturb their quantum behavior. In May 2017, the Aalto team led by physicist Mikko Matanen announced that they had developed just the thing. Their quantum circuit refrigerator takes advantage of a phenomenon known as quantum tunneling, which lets a quantum particle pass through a barrier due to the fact that it functions as both a particle and a wave. As Michael Irving of New Atlas explains, if there is an inducement for an electron to be on the other side of a barrier, such as more energy, it can, in a way, blink through the material to reach it. The team's device is comprised of a superconducting channel and a non-superconducting channel divided by an energy gap. The superconducting channel is a fast lane that lets electrons move with zero resistance, while electrons in the non-superconducting channel move more slowly. Electrons want to be in the fast lane, but only those with enough energy to jump the gap can get there. Electrons without sufficient energy, then, can borrow some from a neighboring qubit. With energy comes heat, and as energetic electrons jump into the fast lane, they take heat with them, cooling the whole system down. In this case, the researchers used superconducting resonators to stand in for qubits, so the next step is to use qubits themselves. Of course, the finicky nature of quantum particles is the reason no one has created a qubit fridge before, so moving to qubits will be no small feat. Even turning off the device has the potential to destroy the superposition. But Matanen is hopeful. Maybe in 10 to 15 years, this might be commercially useful, he told New Scientist. If it's another step toward the quantum computing revolution, we're hopeful too. A team of international scientists believe that new data supports the idea that our universe could be a hologram. That doesn't mean what we see and feel every day doesn't exist, just that we may have to rethink how we envision the universe around us. Think about 3D movies. The images we see seem to have depth, but they're presented on a two-dimensional surface, the screen. Stephen Hawking's black holes blundersters debate. The concept of a holographic universe is similar, in that essentially we exist on a two-dimensional surface, but the information on that surface expresses itself in 3 dimensions. As well, gravity and time don't exist at the fundamental level. It's enough to make your head spin. But the idea of a holographic universe isn't a new one. It was first proposed in the 1990s by scientists Leonard Susskind and Gerard T. Hooft in response to Stephen Hawking's black hole research. As of yet, there has been no conclusive evidence to support the theory. The early universe. The new research looks back almost 14 billion years to a time when the universe was in its infancy. When we go into this concept of holography, it's a new way of thinking about things. Even the scientists who worked on this for the past 20 years don't have the right tools or the right language to describe what's going on, said Skenderis, with the Faculty of Mathematical Sciences at the University of Southampton. It's a new paradigm for a physical reality. When you combine quantum mechanics and general relativity, the best description in terms of this two-dimensional theory, one way to test this result is to take a look at the very early universe. The researchers studied data collected by the Planck Space Telescope, which ceased operation in 2013. This telescope was able to map out cosmic microwave background (CMB) radiation. This radiation presents itself as heat left over from the Big Bang almost 14 billion years ago. It extends outward in every direction, but it's not all uniform. Researchers have looked at these small deviations and mapped them with unprecedented accuracy. The structure of these deviations encodes the physics of the very early universe, said Skenderis. So then the question is, if you have a theory for the very early universe, can you predict the structure of the small deviations? Using the holographic theory, the researchers used mathematical formulas to calculate the predictions. They agreed extremely well with their observations. So while this isn't definitive proof, it can't be ruled out either. In 2015, a study conducted by the Fermilab found no evidence to suggest that we exist in a holographic universe. But if Shorty said that science is constantly growing and learning, any theory, including theirs, could be tossed out as more evidence is gathered. While the whole concept might be mind-blowing, Shorty said that the theory is pretty straightforward. I would argue this is the simplest theory of the early universe. And so far, this is as simple as it gets. And it could help explain everything we see. Shorty. Ready your brain. The universe might be two-dimensional, except we perceive it as three-dimensional, according to the Physical Review letters. In this thought experiment, the flat surface of the universe contains all the information we need to sense three dimensions, much like a hologram. This amazing idea is known as the holographic principle and arises from string theory. String theory says that the gravity in the universe is made up of thin, vibrating strings called gravitons. These strings make up the holograms of events that happen in 3D space within a flat cosmos. They contain the information that a 3D object would have, for example its volume. So if you want to know what's happening inside a ball, you can find out everything you need to know just by looking at the surface. This mind-twisting notion arose back in 1997 when physicist Juan Maldacena proposed the idea that there is a correspondence between gravitational theories in curved anti-de Sitter spaces on the one hand and quantum field theories in spaces with one fewer dimension on the other, says Daniel Grumiller from the Technology University of Vienna. An anti-de Sitter space is a universe where the fabric of space-time has negative curvature, which is often described as being shaped like a horse's. The holographic principle holds in this negative anti-de Sitter space. It can be described in two dimensions, but can be visualized in three. In negative space, you could potentially throw an object in front of you, and it will eventually land behind you due to the negative curvature of space-time. However, anti-de Sitter space has no relation to our universe. The universe we live in is flat and shows some positive curvature properties at astronomical distances. More recently, the holographic principle has been tested mathematically in our own space-time, and so far the numbers seem to match up to reality. The theory tested was quantum entanglement. If two particles are entangled, it means that their properties depend on one another in a certain way, and therefore can only be described as their unit. One depends on the other, and they cannot be described individually. Even if you physically separate the two particles and fling them to opposite ends of the universe, they still remain entangled, and their properties remain dependent on each other. For example, their spin. The physical quantity for the amount the two particles are entangled is called the entropy of entanglement, and this value was the same in both spaces. This result is significant. In order for an up-and-coming theory to gain traction and validity, it has to hold out when the physical constants and properties of the universe are tested. Of course, this is currently only a thought experiment on paper. More calculations and tests need to be done to make grand conclusions about the universe being a hologram, but this initial correlation is very exciting and opens up a new realm of thought and imagination. Whether you decide to embrace the idea that the universe has one less dimension than instinct tells us or not, it certainly draws attention to the importance of blue skies research. This astounding theory was originally only a thought experiment applied to a hypothetical universe. Now, it is possibly changing the way we perceive our own world. The entire disk universe is described by pairs of points on its boundary. Even if the lines were to move around, the information on the pairs of points is sufficient to describe their motion. In a similar, though hugely more complicated way, physicists have suggested that our universe has a boundary and that to describe stuff going on inside it, you only need to describe what's happening on that boundary. It's a strange idea, but it didn't come from out of nowhere. Its origins lie with those gravitational monstrosities we call black holes. A black hole is formed when a lot of mass is concentrated in a tiny region of space. If there's enough mass, then its gravitational pull will be so strong that nothing, not even light, can escape from the vicinity of the black hole, hence the name. Black holes come with a boundary of no return, called their event horizon. Once you pass that boundary, you'll be gobbled up by the black hole, never to return. Physicists initially thought of black holes as very simple objects until a particular problem started to bug them. Were you to fall into a black hole, then, naively, it would seem that your fall leaves the world a simpler place. You're a complex being, and all that complexity would have disappeared forever. Such loss of complexity, of information, is not permitted by the laws of physics, however. It violates something called the second law of thermodynamics. You can test that law out for yourself by not bothering to tidy your bedroom for a while. Left undisturbed, it will soon disintegrate into chaos, that is, greater complexity containing more information. So physicists eventually came around to the idea that black holes aren't just voids, but can be thought of as containing information. But how much information can be contained in a black hole? If you think of information as having a physical manifestation, which it always does, for example in the pages of a book, then the question should amount to asking how much stuff you can fit into the black hole. Obviously, that amount of stuff should be measured by the volume of the black hole. It turns out, however, that the information content, to be precise, the entropy, of a black hole is measured by the surface area of its event horizon. This discovery, made in the 1970s, was the first step towards holography. It suggested that the information content of a black hole is something fundamentally two-dimensional. Physicists later went on to suggest that the same goes for ordinary regions of space. Like with our disk universe above, whatever is going on inside them can essentially be encoded in a two-dimensional boundary surface. If this is the case, then our three-dimensional description of physics overshoots the mark, and we should be able to get by with a leaner version. In 1997, developments in this area inspired Juan Maldacena, only 29 that I am in at the time, to create a toy universe described by mathematics that is entirely determined by a theory defined on its boundary. Like the real universe, this toy universe contains fundamental particles that can be described mathematically. But each of those fundamental particles has its counterpart on the boundary, also described mathematically, and every interaction between interior particles corresponds exactly to an interaction between boundary particles. You can now describe the action of, say, dropping an apple in the interior purely in terms of the boundary theory. You can even choose to ignore the interior altogether, without losing any information at all. In this sense, Maldacena's toy world is a hologram. So far, so similar to our disk universe above. But there's an added, and very important, attraction. The boundary of Maldacena's world is described by a quantum field theory. That's the kind of theory used to describe the smallest building blocks of matter, such as atoms and subatomic particles, and their interaction through the electromagnetic force and the strong and weak nuclear forces. Crucially, quantum field theories can't describe the force of gravity. This failing is one of the biggest problems of modern physics, and it makes Maldacena's invention all the more amazing, even though it is generated by a gravity-less quantum field theory defined on the boundary. The physics in the interior of his universe does include the force of gravity. For those familiar with the area, it is described by a string theory. Thus, in Maldacena's universe, gravity emerges holographically. so the work may contain a clue as to how quantum physics and the theory describing gravity, Einstein's general relativity, may finally be reconciled. Maldas in his work described a world very different from our own, but since then physicists have come up with theories that could potentially apply to the universe we actually live in. It's these kind of models that were tested in the new research. The team behind it, Nyasha Shorty, Claudio Coriano, Luigi Del Rose, Elizabeth Gould and Kostas Skenderis, worked out what holographic models of the very early universe would imply for the structure of the cosmic microwave background. They then compared these kind of predictions with the real cosmic microwave background and found that a holographic universe could indeed be possible. Holography is a huge leap forward in the way we think about the structure and creation of the universe, says Skenderis. Scientists have been working for decades to combine Einstein's theory of gravity and quantum theory. Some believe the concept of a holographic universe has the potential to reconcile the two. I hope our research takes us another step towards this.